Welcome to Chapter 7 of University Physics. Chapter 7 of Physics with Calculus, going over the University Physics OpenStax textbook, Volume 1, Work and Kinetic Energy. We'll be going over the slideshow as we've been doing for the previous chapters. It's a back and forth between the OpenStax curated slideshow and examples from the text. I will be going over selected problems. If you at any point would like to go over further problems, pause the video, go through the problems in the book, return to it. This is not meant to be your only source of this information. Feel free to go to any other means to help you understand and convey the knowledge as you see fit. If you have any questions, comment down below or send me an email. Same spiel I give before every lecture. This chapter is pretty short and sweet. It's going over applications of the ideas and thoughts in the previous 4 or so chapters. So we're going to go over work, potential, kinetic energy, power, things along those lines, and a couple quick applications. So let's begin. So what is work? Well, in a basic sense, work is not the way that we commonly talk about it. Physics really likes to have equations for things. Physics really likes to have answers to questions. And therefore, we define work in a very specific way. Namely, work represents force over distance. If you apply force to something and it moves some distance in some way, shape, or form, you do work. Walking is work because you're moving someplace. Standing technically is not work because you're not moving anywhere, right? You could be carrying something, you could be holding something very heavy, but you're still not working, according to that strict definition of physics as we're talking about here. We define physics by the equation shown below here. The dW, or some increment of work, is defined by a force vector, see the arrow on the top there, measured through some infinitesimal displacement, dr vector. And you dot product these two vectors together to get the equation shown below. Cosine theta there represents angles, because we really only care about the component of the motion as defined by the force pushing it in that direction. So if we care about the displacement in the x direction, I only care about the motion in the x direction, for example. We tend to think of this as an x direction thing, which is why it's a cosine. Right? So to find the answers to the work, we're going to integrate our force with our distance, essentially, our dr vector. And the path traveled is the a and b of said integral. Here is a description of what I'm talking about here. So we have some force in some direction. And think back to what an integral is, think back to what a differential is. The path taken to get from A to B is defined, the work done is defined at each one of those points based on that force and based on that direction. This is a straight application of kind of the first thing you learn in calculus, right? This is a straight application of those concepts. Here we have different examples of people working, people not working. As I said before, if you're standing and not moving, your distance covered is 0, so your work is 0, regardless of the force involved with it. As soon as you start to move, then you therefore have some level of work involved. And if you're pushing an angle, as A is shown above there, then your work done is respective to the x direction or the cosine theta of said angle. So let's go over an example in practice of this concept. Example 7.2. Again, I always say this, reading the book helps. If you're not understanding what I'm talking about, you should go through the text and see if you can get a better grasp of what I'm discussing here. The equations, I would say, relatively straightforward for this section, so I'm confident in your abilities, but if you need extra help, that's perfectly fine. Find the extra help. I'm here. Your classmates are here. Lots of videos on YouTube about physics from a calculus standpoint. All right, so you're moving a couch. You decide to move your couch to a new position on your horizontal living room floor. The normal force on the couch is 1 kilonewton, and the coefficient of friction is 0.6. We talked about friction last chapter, right? It's the force that impedes motion. You first push the couch 3 meters parallel to a wall and then 1 meter perpendicular to the wall, as shown in this image here. 3 meters parallel, 1 meter perpendicular. How much work is done by the frictional force? So at coefficient of friction, how much work is that friction doing? You don't like the new position, so you move the couch straight back to its original position, path B, orange path. What's the total work done against friction moving the couch away from its original position and back? So this is a Pythagorean's theorem conversation, but I care specifically about friction involved. So I have to go back, think about our equations of friction. The couch is moving, so we have kinetic friction. The equation for kinetic friction, of course, is mu k times n, the normal force, is your force of friction. So we need to take that and rearrange it to be the work of friction, which is given by the force of friction times the distance covered. All right, cool. So we're given coefficient of friction, mu, as 0.6. We know the normal force of the couch, right? 1 kilonewton. Can we solve this stuff? Yes, we can. The first answer is we're moving 3 meters and then 1 meter horizontally. So how far are we moving? Well, the work done is equal to the force of the kinetic friction, which is mu k times n, so 0.6 times 1 kilonewton, plus the distance. The distance covered is 3 meters and then 1 meter, 4 meters total. That gives us the work done by the friction based on these components, or negative 2.4 kilojoules. Cool. So what is the length of the hypotenuse? Well, Pythagorean theorem, a squared plus b squared equals c squared. So the square root of 3 squared plus 1 squared. And then we can add that friction into what we've already discussed, which is a 3 and the 1 there. And we end up with a total of 4.3 kilojoules in the positive direction. Why is it positive? Well, because we're spending a lot of friction pushing it back, right? So the motion, the path of the motion is the opposite direction of where we started. That's why we have a positive kilojoules there, right? Total work is not zero, even though the total displacement is zero, because the thing moved. Work is defined by movement. When you put force into something, if work is coming out of it, something changed. That's something we tend to call, in this case, movement. And you can go over this exact conversation in many different ways with many different variables and vectors. You all always, however, using the same conversation. How far did it move? How much force was I put in to make it move? Right? Here we can talk about physics loves its infinitesimal particles, right? So let's look at an example using a particle. So here you have an example of using x, y, and z in your work, and it's simply the x and the y and the z components. I keep reiterating this because we're looking at the topics we discussed in previous chapters, and we're slapping a fresh new coat of paint on it. Instead of movement in the x, y, and z vectors in the x, y, z components, we're talking about work. So it's your distance times your force in your x, your force in your y, and your force in your z. If you take good, diligent notes and write down your knowns before you start, you'll be able to follow this process to completion. I keep harping on the same idea because that is the key to success in all of these things. Don't assume you know something. Go ahead and write it down. Pencils aren't that expensive. All right, so work done by a variable force over a curved path. Variable, right? We're entering physics here. An object moves along a parabolic path, as shown down here, to the equation y equals 0.5 x squared. From the origin, 0, 0, to a point B, which is 2, 2 meters by 2 meters, under some force, as shown here. The force is 5 Newton meters in I hat plus 10 Newton meters J hat. Calculate the work done going from point A to point B. Interesting. So we can look at this question and we can say the components of the force are given functions of x and y. useful, right? We can use the equation of the path to express y and dy in terms of x and dx. Namely, a y component is in relation to 0.5 x squared, right? Because the y component has the I hat on there. And our dy, there would be 2 times that 0.5 x dx because we integrated it, right? So we differentiated it, right? X squared comes on down to a 2 in the front. You know your calculus, right? So, oh wait, I said the I have, my bad. The original equation. There we go. A y is our original equation. Our dy is the differentiation of it. So given these two equations for y and dy, we can figure out the work. The work here we're dealing with, we call it infinitesimal, so it really doesn't matter for the conversation, right? So we know that the work done is equal to the force times dx plus the force in the x component of the force, there we go, times dx plus the y component of the force times dy. Well, I know the x component of the force and the y component of the force because they're given to me right here in this equation, right? The x component of the force is 5 Newton meters because that's the I hat, and the y component of the force is 10 Newton meters because that's the j hat. So 5 Newton meters times y, because that's the part of the equation, right? Times dx plus 10 Newton meters x dy. Fantastic. Plug and chug in what I know. I know what y is, right? And I know what dy is because I calculated those out given the equation I was given. Right? So we have our equation here. Figure out unknowns, figure out unknowns, solve. We've been doing this for how many chapters now? Plug in as the equation is shown here, our 5 Newton meters, our y is 0.5 x squared, and then dx. And then here's our 10 Newton meters, which was our force in the y direction, times x, which is given by 2.5 x squared, and then our dx that is shown. Sweet. Plug everything together. We land on an equation of the infinitesimal element of the work as 12.5 Newton meters squared x dx. Now we can integrate that over a distance, which is 2 meters, right? And when we integrate that, I'm not going to go over how to integrate things. We can plug in our 2 at the end of our integration and land on a total work done of 33.3 joules. Now, what is a joule? The joule is the unit of work, and it's basically a Newton meter or Newton meter squared in this case. So when you end up on, I didn't really cover that, did I? No, skip that part. Unit of work is the joule. If you end up solving for joules, if you end up solving work equations, you put it in joules. There you go. Because that is the amount of work done. Again, Newton meter squared because dealing with the 2D as opposed to the 1D shown as in the example at the top there, the moving of the couch. I keep stressing this because I think it's very useful and very crucial. Remember, you know, if you find your equation, you write down your equation, write down your knowns, solve for your unknowns, it's laid out in front of you. Remember, sometimes you have to adjust the equations, differentiate out to get changes in y versus placement in y and all that jazz, but very doable. Springs fall under the same idea. Springs have their own equation, which I'm presenting to you right here. Just look it up. And springs care about a constant, usually written as K, which is part of Hooke's law, shown here. K is a known given the material of the spring. In this case, the dx, the displacement of a spring, is defined by how much the spring compresses or expands. So K is either known or K is what you're solving for. dx is the change in the spring, and then the amount of energy by pushing in or pulling out the spring is given by the force equation as shown here, negative K delta X. This, as we said before, is calculus. So what are you solving for in these instances? Well, you're solving for the area below the change in work. For the spring here, for example, you're solving for the area of the equation created by the force with respect to time. I'm sorry, with respect to distance. There we go. These things can have positive and negative values, of course, which is dictated by direction, as we've talked about countless times. And a spring is a good example of this idea in motion. As a spring bounces back and forth, it's increasing and decreasing its energy based on the motion of the spring. The spring is, when the spring compresses, work is being done. When the spring expands, work is being done. We differentiate those with the positive and negative, but it's, as it oscillates back and forth, it's decreasing in a manner dictated by the spring constant, what it's made of, how much it's compressed, all those various components. And all of that falls back down to negative kx, negative k dx. All right, so that is work. Hope that landed. It was a quick go by, but it's a quick concept, right? It's an equation, force times distance, or with spring constant times distance. Let's move on to kinetic energy and, by association, potential energy. Kinetic energy is given by the equation 1/2 mv squared. So how big something is and how fast it's moving tells you how much kinetic energy it has. The bigger the thing, the more kinetic. The faster it's moving, the more kinetic, right? Indiana Jones being chased by a giant round boulder squishes him, right? Getting shot by a little tiny bullet still kills you. That is kinetic energy, and it works. You can, of course, relate this to other various things, such as momentum, for example. Just plug and chug in your replacement values, as shown here. Kinetic energy is equal to the momentum squared over 2m, m being the mass. It's write down your equations, solve them out when it needs to be solved out. So let's talk about this, and it's connected to the reference frames. Again, reference frames are very important when we get to higher level physics. You need to know what you're talking about compared to other things because you can have different results. Here's a good example of that concept. So a person is on a train. A 75-kilogram person walks down the center aisle of a subway car that's traveling at 1.5 meters per second relative to the car. Whereas the train itself is moving 15 meters per second relative to the tracks. So can you calculate that person's kinetic energy relative to the car, the train car, relative to the tracks the train is moving on, and relative to the kinetic frame that's somehow attached itself to the person? So it's a kinetic frame is moving with the person. What is kinetic energy? Well, C is one of those difficult sounding questions that should be super easy. If your reference frame is moving with your individual is not moving within the reference frame. If you're not moving, your velocity is zero. If velocity is zero, your kinetic energy is zero. So C is super easy. Skip that one. A and B, however, can present a bit more of confusion because the person's moving on the car and the car is moving. So we have different levels of energy with respect to those two things. The person's only moving 1.5 inside the car, but the car itself is moving 2. So you got to add those two velocities together, essentially, right? So we can use the equation 1/2 mv squared to calculate these things, shown here. However, in part A, we need to realize the reference frame, which is the car itself. Not the tracks, not the outside world, just the car. So what do? Well, if the person is moving and the car is not moving, then the person is the only velocity we need to care about. So the kinetic energy is equal to 1/2 times its mass, 75 kilograms, times its velocity squared, which is 1.5 squared. The person, given that the car essentially to the person is not moving, has 84.4 joules of kinetic energy when he's moving. However, we're going to keep in mind, as the picture dictated here, we're not describing the way the direction the person's moving, right? It's the person moving up or down the car. Well, that doesn't really matter because the car is essentially stationary for this reference frame. So I don't care about that part. But when I go down to B and solve for the person's kinetic energy relative to the tracks, suddenly it plays a big factor. If the person's moving with the train, he's moving faster in reference to the tracks than if he's moving against the train's motion. How does that pan out? Well, we just need to solve for the person who entered the tracks by either adding his 1.5 to the car or subtracting his 1.5. If we subtract his 1.5, we get less kinetic energy than if we added his 1.5. And noteworthy, both of these numbers are a lot larger than him moving within the train as my reference point. This is because the speed, 15 meters per second, is an entire degree, an order of magnitude faster than the person. So the kinetic energy is also an order of magnitude greater. Also noteworthy here, I'm not asking for the mass of the train because the reference point is the person to the tracks, not the train to the tracks. Right? That's where the subscripts in here come in. The V subscript PC is person to car, train car, and the VCT is car, train car, to tracks. So if I'm caring about the person with respect to the train, the tracks, the car cancels out. You remember doing that a chapter or two ago, where if the center number letters are the same with reference frames, you cancel them, right? We've covered a lot of these concepts already. We'll cover them in different ways now. So that was kinetic energy. Next thing is power, right? Oh, work energy theorem. Okay. So we've discussed work. We've discussed kinetic energy, how these things all come together. Or as shown here, what is this horse doing in reference to the hay bales or what are those salt blocks, I think? In reference to the salt blocks, in reference to energy dispersion, stuff like that. Because there's a lot going on in a picture that's shown here. A lot of cool math and science and equations beyond the power of the horse. Your work energy theorem describes your net work done on a thing, on what you're talking about, the network, and it relates the energy used or the energy given back by said system. Big equations shown here, right? We got our change in work. Network is given by a net force times some distance, as we talked about before. And then if we incorporate Newton's second law of motion, F equals ma, to that conversation, our net force is given by our mass and our velocity. So our net work cares about our mass, our velocity, and our change in displacement, our dr vector, right? So we can take this equation, rearrange things to our liking. In this case, as shown in the center here, we're keeping the dv up top and throwing the dr in the bottom there. Sorry, we're sliding our dv over and we're throwing our dr on top. How multiplication works, right? And then we can extract out an equation for our change in net work based on our mass, our vector of velocity, and the change in the vector of velocity, which is a useful thing to have. So utilizing that dot product allows us to integrate over the x, y, and z components of our velocity and our changes in velocity. And when we do that, we come across kind of an obvious statement, which is the amount of work done to a system is directly related to the amount of work expelled minus the amount of work put in. Right, kind of obvious, right? How much the amount of energy expelled minus the amount of energy put in. So you start with a tank of gas, you end up with half a tank of gas, therefore you used half a tank of gas to do the thing, right? Lots of complicated math to verify this idea, but that's essentially the work energy theorem. So the net work done on a particle equals the particle, of course, not mean particle, meaning the thing you're talking about. The net work done is equal to the change in the thing's kinetic energy. So how much energy is being expelled by those horses dictates how much work is being done by those horses. So you don't actually need to know specifically force and change in displacement if you can solve for kinetic energy associated with these concepts. So you got like 4 or 5 different variables that all can give you the same conclusion. You can always answer the question based on what variables you're given. This can be useful for a variety of things. Classics include, toy car loop to loops, going over and under a loop. What happens in that scenario? Are you gaining or you're losing energy? All that jazz. I'm going to focus instead on this example, which is the energy exerted by a bullet being stopped by something, in this case, a wood block, as shown here. So again, the point of this chapter is you can determine work via kinetic energy. You don't need to know forces and displacements. It's because sometimes displacement isn't the important part of the conversation. A bullet has a mass of 40 grams, 40 grains, or 2.6 grams, and a muzzle velocity of 1,100 feet per second, or 335 meters per second. It can penetrate 8 1-inch pine boards, each with a thickness of 0.75 inches. What is the average stopping force exerted by the wood? So it's a bullet that goes through all the wood. How much stopping force was exerted by said wood? So what do we know here? Well, we know a lot of different stuff, right? We know the weight of the bullet. We know the initial velocity of the bullet. And we know the thickness of how long it took to stop. 8 1-inch pine boards, each with a thickness of 0.75 inches. That's how long it took the bullet to stop. Can we solve this problem? Can we figure out the stopping force, right? What does that mean of this whole scenario? Well, we can assume under the general condition stated that the bullet essentially loses all its kinetic friction going through the wood, right? So the work-energy theorem says the initial kinetic energy is equal to the average stopping force times the distance penetrated. So the force, we go up to the top here again, the force times the distance is our dW net. So if we can figure out the dW, where you at again? There we go. You can figure out the work done. You can figure out the force that caused that work to be done in that distance. That's what we're solving here. The change in the bullet's kinetic energy and the net work done stopping it are both negative. So when you write the work energy theorem, the net work equals the average force time of the stopping bullet to see what you get. So convert over to SI units, right? You have 8 3/4-inch boards, which is about 15.2 centimeters. So a DR is 15.2 centimeters. And we know that a net work, since the thing stopped, both answers are negative. So we cancel out the negatives. It's just a little quirk of physics and solve what we need. So the force average is given by a 1/2 mv squared. Since the kinetic energy at the end is 0, we only need to care about the kinetic energy at the beginning because the change in kinetic energy is whatever it was to 0. It started out with 1/2 mv squared, and then the amount of distance it took to stop was 0.152 meters. So we are combining this equation relating to kinetic energy, since KB is 0, or the end of the travel, you have 0 kinetic energy because the bullet stopped. Ka is the only thing we care about. So our net work is equal to negative Ka. And that negative Ka is equal to F net times dr. So divide out dr, which is the distance traveled, and we get 960 newtons. So the stack of wood applied 960 newtons of force to stop the bullet. You're given the questions. You need to know what numbers go where to solve the problem, right? You can keep doing this in lots of different examples. Here's pull-ups. Last thing we'll discuss here is power. What is power? Well, that's how much work, that's the amount of time it takes to do your work. It's real simple conversation. dW over dt or delta W over delta T if you don't want to talk calculus. So you can integrate those out, of course, to get your answers. And it's just another equation, another variable that can be involved in all this stuff. All these questions are revolving around the same basic topic, which is that energy thing we've started talking about in like chapter, 3 and 4, right? So let's go through this quick example. You see the stuff really isn't that bad. And then I think we'll be done, actually. So how much power must an automobile engine expend? Again, power in terms of the physics of it. So it's work divided by time is equal to power. How much power must an automobile engine expend to move a 1,200 kilogram car up a 15% grade at 90 kilometers per hour? And I said then do everything in SI units. Assume that 25% of the power is dissipated, overcoming air resistance and friction. Now that we're getting more and more complicated questions, we cannot forget things like as friction and drag and stuff like that. In this case, they're giving you just a blank percentage to deduct from your answer to give you what you need. But you have to keep that in mind if I ask you a question, or if you see a question where certain things are not explicitly stated, such as friction, or explicitly stated you don't really care about them, you need to consider that as part of your conversation. So the car is moving at constant velocity, so we don't technically have a difference in kinetic energy. Because kinetic energy is directly related to velocity. If velocity does not change, kinetic energy does not change. So net work done on the car is 0 because our kinetic energy is A and B of the kinetic energy is the same. Therefore, the power must be supplied by the engine to move the car equally to the power expended against gravity and air resistance. What's that saying essentially is we're not gaining anything going up the hill, right? By assumption, 75% of the power is applied against gravity, which equals equation shown here. The mass times gravity, dot product of the velocity, whereas the dot product of velocity is v sine theta, given our 15% grade. The 50% grade is equal to the tangent of theta, so we can infer out from that the following equation. Power is equal to a mass times the gravity times the velocity times the sine of that 15% grade. And when you solve out your power, figure it out, multiply it by 0.75 to get your kilowatts of 58, or about 78 horsepower if you need to translate to American units. So where's that sine theta coming from? Go up here to my examples. That's not the example I wanted. Oh, okay. So your sine theta is referencing to your grade here because you need to have that x component, and our velocity is given by our 90 kilometers per hour. So your tangent inverse of theta gives you SOHCAHTOA, opposite over adjacent. The tangent inverse of theta gives you your height, which is what you need to solve for the solve your velocity vector. Sorry, a lot of V's there. Remember your trigonometry, essentially, right? And that's actually the entire conversation, right? Work and power and kinetic energy are all pretty simple, not simple, I'm not going to use the word simple. They're all pretty rote equations that when you're asked questions about them, go back to what you're go back to your book, find the relevant equation, and then plug in your numbers. If you get lost someplace, write down your knowns and look for your equations that have those knowns in them. I think this book, actually, the appendices have like every equation used in terms of and organized by what you're talking about, which is super useful, right? And yeah, hopefully you won't be too caught up by weird stuff. With that being said, thank you for listening in. You got any questions, feel free to let me know. And take care.